you.
We are already in page 2. So, okay, we have now the last talk of this morning by Shoji Hashimoto about tests of the operator plot expansion through lattice QCD. Thank you.
So it's a sort of continuation of the discussion on the spectral function, but from a different perspective. I mean, the lattice calculation. As you probably all know, the basic quantity, that the most important quantity that we calculate on the lattice is the correlation function. And that is just a first principle calculation. So it's not limited to the long distance region where we extract the lowest lying hadron masses and its properties. But also you can use the same set of the calculation to analyze the short distance behavior of the correlation function. So my talk is about the short distance correlation functions. So I will mostly discuss about the current correlator, and then briefly discuss on the Dirac operator eigenvalue spectrum and also the Charmonium correlator. And if I have time, I've mentioned about the related the subject, which is the inclusive B-meson decay analysis. So we are working on the Euclidean lattice. So for us, the easiest way to analyze is to go to the coordinate space, Euclidean coordinate space. In the coordinate space, the operator product expansion looks like this. For the current correlator, it has a dimension of 6. So at short distances, it has a divergence as 1 over x to the 6th power. And this is the perturbative contribution for which the perturbative expansion is known to alpha s to the 4th power. And in addition to that, there is a very small quark mass correction and also the leading power correction that is expected from the operator product expansion, and that has a 1 over x squared dependence on the distance between the two currents. So the question is whether this type of the theoretical expectation is really confirmed, can be really confirmed using the lattice data. But it's not that simple because the lattice QCD has the problem of the discretization effect at very short distances. So we need to find the region where the distance is large enough compared to the lattice spacing, but still small enough to apply the perturbative QCD calculation. So we first little bit discuss about the discretization effect. By the way, these are the lattices that we use, but it's a kind of details. So we think about the scalar correlator, pseudo-scalar correlator, as well as the vector and the axial vector correlators. For the vector and the axial vector, just for simplicity, we consider the components where the mu and the nu are set equal and summed over from 1 to 4. And we always consider the non-singlet, flavor non-singlet operators, so we do not have the disconnected diagrams. And we are using the chirally symmetric lattice action so that the scalar and the pseudo-scalar become equal when the non-perturbative correction is eliminated. The same for the vector and the axial vector current. Of course, in the massless limit. So this is the first look at the lattice data for the pseudo-scalar current correlator. Obviously, there are scatters of points, and by the way, those red points are the lattice results while the blue points are the just free correlator. So you can see that how significant the discretization effect is. It's points are just jumping around. But if you carefully look at, you can see that there are general trend that the lattice data are about following the structure of the free correlator. So the discretization effect is essentially given by already by the free correlator. So the easy simple idea is to subtract the known discretization effect by having the difference between the lattice and the continuum in the free case, and the subtract this piece from the lattice data. Then we obtain this type of smooth function that we can compare with the experimental data. But now this is still the logarithmic scale. So if you look at the very details, you still see the large discretization effect. So in order to avoid such significant discretization effect, we simply take some points that is separated in not in the x direction or y direction, but the close to the direction to the 1, 1, 1, 1 in the four-dimensional lattice. That has the smallest discretization effect. So we ignore all the other points and finally get this kind of a smooth function. This is the pseudoscalar correlator times the x to the 6th power. So it looks like a smooth function, and that we want to compare with the perturbation theory. So this is the perturbative side. The perturbation theory is known by, is calculated to the alpha s to the 4th power by these people. That is given here for the scalar and vector cases. And it's written for MS tilde scheme that I forget what it means. Is that some details less. But anyway, by using this type of scheme, the convergence of the perturbation theory is not very nice. But if you look at, for instance, the vector piece, the one loop is written there, the two loop is there, three loop, and four loop. So they are jumping around. So the convergence is very bad if we naively use this scheme. But there is a way to improve it. That is the classic BLM scale setting by absorbing some part of the higher order terms by changing the scale in the coupling constant. One can improve the perturbative expansion from this one to the other one. And you can clearly see that the coefficients are much smaller. By doing that, we obtain something like this for the scalar cases. On the left-hand side, the previous scheme, and now by choosing the better scale, we see the nice convergence from the one loop, two loop, three loop, and even four loop. So we use this to compare with the lattice data. Yes. I'm sorry. For the scalar current, that is scale dependent. For the vector and the axial vector, it's scale independent. But the scalar current itself has a scale dependence. So it changes. So the comparison is like this. Those are for the scalar and the pseudoscalar, and the lattice data are shown by the red and the blue symbols, and the continuum is of course independent. Is the same for the scalar and the pseudoscalar, and that is it's like this. So it looks like the perturbation theory nicely works, or the lattice calculation can actually reproduce what the perturbation theory predict, at least for the average of the scalar and pseudoscalar. And the same thing, similar the plot for the vector and the axial vector, and here the consistency is not that great that we can see some more details later. By using by looking at the difference between the vector and the axial vector, one can be sensitive only to the non-perturbative corrections from where you can actually extract the chiral condensate from the OPE. If we do that, we obtain this kind of data that is consistent with the nominal number that is known for some time for the chiral condensate, 250 something MeV cubic. But there is an important inconsistency between the lattice data and the operator product expansion. For this particular quantity, the pseudoscalar minus the scalar, or the axial vector minus vector, if we look at it very carefully, this is the lattice data. And what we know from the OPE is that the coefficient is smaller for the pseudoscalar minus scalar compared to the vector minus axial vector. But the lattice data suggests the opposite, and there is a significant x or the distance dependence. So it means that the leading or the operator product expansion doesn't really work to explain the real non-perturbative physics. Probably the higher orders are important. This is not the new observation that has been known for some time, starting from this famous paper in 1981 by those people. And the spin zero correlation functions may deviate from the OPE at short distances. I do not really understand what is written in that paper, but that is somehow known for some time. And this is Shuriak's review paper that also suggests the same thing. And here the pseudoscalar correlator is plotted for the pions and kaons, and that is very different from the QCD sum rule SVZ. That curve is there already 0.3 Fermi or so, that you see the strong deviation from the OPE analysis. And our lattice data also suggest the same thing. Those are about the purely theoretical comparison between the lattice and the perturbation theory, and now we go one step forward, including the experimental data. You already see this type of plots many times this morning, so I don't have to explain it. But in order to use it to compare with the lattice data, we do a kind of Fourier transform of the experimental data by using this type of formula. It's a kind of spherical Fourier transform from the momentum space to the coordinate space. Then by using the Bessel function, I can do it. And starting from the RF data on the right-hand side, I obtain the coordinate space current correlator that is expected from the experimental data that is shown there. So that I can compare this with the lattice calculation. Now the same thing is plotted, but x to the 6th power is multiplied, so that at x of 0 it becomes 1. Then this is how it looks like. Those are the vector and axial vector that is reconstructed from the experimental data on the right-hand side. And by the way, in order to do this, I need the experimental data up to the energy of infinity that doesn't exist. So I have to use some sort of perturbation theory to supplement the data above some point. And we know that there is some duality violation, potential duality violation contribution. So I assume that. And the difference is actually very small when we move on to the coordinate space. That is the now famous exponentially suppressed duality violation effect in the Euclidean space. So that is a difference. The hatched curve and the green curve, those are almost the same. So we have this, and that we want to compare with the lattice calculation. I can skip this. Actually, this. For the vector plus axial vector, lattice data are shown there on the top right, and there the gray band is the same curve that is obtained from the experimental data. And except for the region where the discretization effect is huge, we can somehow reproduce the experimental data for the V plus A, the average combinations. On the bottom, I plot the V minus A. Here, the perturbative contribution simply cancels out. So everything is non-perturbative. And again, the lattice data are shown there, and together with the sort of experimental data, reconstructed curve, that is the band there. And you can also plot the expectation from the operator product expansion. And here, the dimension 4 OPE is shown there. That is far too small compared to the experimental data or the lattice. And the dimension 6 is, on the other hand, there. That is too large. So it means that already at 2 point, or let's say 0.3 Fermi, the deviation from the operator product expansion is seen in the coordinate space. Yes. One by one. I'm sorry. Lattice data. Well, you are right that the lattice data are very correlated, but we don't see the significant deviations. That is what I mean, other than the points over there.
And also the ELF data will be very strongly correlated.
Yes.
So a lot of differences will probably be.
Okay. And
so what is delta x?
The size of the bin. We have so many points on the coordinate space, but we put them together in some small bins. The size of the bins, so it's not so much. So this is it. I'm not arguing about any violation or anything of the operator product expansion, but what I want to say is that we can do something like this. This is not the end of the story, and probably for many other quantities, we can use the lattice QCD to test the perturbation theory and the operator product expansion. That is what I wanted to say. So for example, we can think about the completely different quantity, that is the Dirac operator eigenvalue spectrum. What is it? We have the Dirac operator, D slash, and for a given gauge field background, you can consider the eigen equation like this one. This slash psi is I lambda psi, and there are eigenvalues lambda, and so you can think about the spectrum of lambda, eigenvalue lambda, and if you average over the gauge field, then we get the spectral function of the eigenvalue. That is my definition of the Dirac spectrum. That's completely different from the previous row. That is the vector and the axial vector, the density of states. But here is the density of the eigenvalues. And the very famous very famous relation about this is the Banks-Casher relation that relates the spectral density at 0 is essentially the chiral condensate. And another well-known fact is that at high energies, the spectral function behaves as lambda cubic in a four-dimensional theory. And the perturbative corrections to this limit is known up to alpha s to the cubic by these people. But actually, this is obtained from the calculation of the one-point function. It's like a one-loop chiral condensate calculation. But by putting the mass of I lambda, we can obtain, and taking the imaginary part, we can obtain the spectrum. That is a trick used to obtain that perturbative expansion. So this is our lattice data on the top left. As a function of lambda, the density is shown, and at near 0, we should have some finite density that corresponds to the chiral condensate, but in this scale, that is too small to see. Starting from here, I want to look at the power, how much it deviates from the lambda cubic. I defined the derivative of the log to see if it deviates from 3. And actually, this is the data. And the non-perturbative, by the non-perturbative calculation, I see that this is certainly smaller, significantly smaller than 3. And we see the larger and larger deviation at lower energies. That we can compare with the perturbative calculation. Those are shown by the many lines, but this is the same thing. Now the lattice data are shown by the colored points, and the perturbative expansion is given by those lines. For these quantities up to alpha s to the 4th power, the coefficient is known, and the last one I use some nominal value of the coefficient. So you can see that the consistency is very nice, up to around one JeV or above. But going down to several hundred MeV, you see the non-perturbative effect. That is another quantity where we can see the consistency between the lattice calculation and the perturbative calculation. Cyber psi is yes, it is renormalized using renormalization factor is ZS. It's the same as the scalar density operator. So I use some continuum scheme, MS bar scheme at some scale. So yes. So we should expect some non-perturbative correction to that, but unfortunately the detailed calculation of the operator product expansion is not known for this quantity. And naively, by the dimensional counting, I expect that the leading non-perturbative correction is something like psi by psi times some constant. Because it is just a dimensional ground, and this is the lowest possible operator. But if we have it, there is no lambda in front of that, so there is no dependence on lambda. So this term doesn't affect the power that is the derivative of this quantity. So the previous plot, in the previous plot, the leading non-perturbative correction in the OPE doesn't show up. So some higher order corrections are responsible for the deviation from the perturbative calculation. That has to be, yes.
What exactly is the lambda that you're using? So it's the improved overlapping lambda? The spectrum is complex.
Yes, we use the domain wall fermion, but the details, very detailed definition of the operator that has to be discussed personally. There's so much detail. So. I'm sorry. Those are about the Dirac operator spectrum, and using the same quantity, I can obtain the alpha s by fitting the, is it 5 minutes or 5 minutes? 5 minus 505. Yes. Using the same data, I can extract alpha s, and bin by bin I obtain those data, and by averaging those all bins I obtain this, and unfortunately, first of all, this is consistent with the known value of the alpha s, but unfortunately the error is several times larger than the current best determination. So we can't compete in this way, but there is another quantity that we can eventually use to extract alpha s. That is another interesting thing to look at. Okay, now in the remaining 5 minutes or so, I discuss on the Charmonium correlator, and this has been already discussed by Peter, I think, on Monday or Tuesday. For the Charmonium correlator, we can use the Cauchy's theorem to relate the experimental data to the correlation function at q squared equal to 0 and its derivatives, and that can be calculated using lattice QCDs, and on the coordinate space that is related to the some time moments of the correlator. So for this particular quantity, the nice thing is that we can use the experimental data and the lattice calculation as well as the perturbation theory to calculate or extract the same thing. So it is done here, and the analysis of phenomenological analysis uses this experimental data to obtain the Charm-Coke mass, for instance, or the alpha s by comparing the experimental data and the perturbation theory, and that already started in the 1970s. But in the lattice community, the same quantity was first used by the HP QCD collaboration to determine the Charm-Coke mass and alpha s. And of course, we can also compare the experimental data to the lattice calculation, and by doing that, we obtain something like this. This is some moments constructed from the experimental data and also calculated in the lattice QCD, and those in nice agreement you can see here. This is the lattice data, and the phenomenological or experimental data are shown there. So for this particular quantity, we see the nice triangle among the experiment perturbation theory and the lattice, And that is a sort of ideal situation that we can use as much information as possible to obtain the fundamental quantities. And the similar sort of idea may also be extended to some other quantities like inclusive B-meson decay. I do not discuss in details, but the main idea is that we can use the same sort of the optical theorem or the Cauchy's integral to relate the experimental data and the lattice calculation somehow in the Euclidean space. I probably want to skip this, but the previously for the Charmonium correlator, we look at the current correlator, and that is the experimental data is available as a form of the spectral function, and the lattice calculation can be done for this particular quantity in the Euclidean region that is related by the Cauchy's theorem, and the same thing can be done for the inclusive decays. That it is more complicated because there are two kinematical variables, but fundamentally those are the same thing. So the analytic structure of the function is much more complicated, but the conceptually they are essentially the same thing. So I personally want to extend this kind of idea to other more complicated quantities. So I'm about finishing. We can test the operator product expansion using lattice QCD. Once the lattice QCD calculation is available, you might think that there's no use of the operator product expansion anymore. We have the non-perturbative calculation, but it's always nice to have the analytical control or the qualitative understanding of the behavior of the quantity. So it's very nice to have the comparison between the known theory and the lattice. And we have more applications, and I am now thinking about the inclusive processes that using that is QCD. And so I want to finish. For many quantities, I wish to have this situation that experiment and perturbative QCD and the lattice, we work together. Okay, thank you very much. It's on time. Yes.
Okay, thank you very much. Any questions? Maybe better if you already asked.
Okay, so I just was wondering, when you compare the lattice results with RF data on the correlation function, how do you treat the lattice artifact? So I understand that you take kind of the diagonal elements and that minimizes the scattering, but that by itself doesn't mean that that's kind of continuum result. So do you take a formally continuum limit, or how do you treat the lattice artifacts?
Eventually, we need to extrapolate to the continuum limit. In order to do that, I first put the lattice data in a small bins of x, and then for each x, I consider the continuum extrapolation. And for those quantities, that extrapolation is essentially constant. I don't even see the a squared.
So you don't see discretization effect? That's the statement.
After choosing the points as described there.
Mm-hmm. Yes. Okay, thanks.
Yeah, can you go to your V minus A OPE convergence slides?
This one?
Okay, so I don't know if you've done this. I'd be curious to know. So obviously in the chiral limit, the dimension 4 term goes away and you're dominated by the dimension 6 in the OPE. And so your figure does nonetheless show slow convergence in the sense that a dimension 6 dominant contribution doesn't work for very far. But an interesting question, if you've done it, is what happens if you try and fit the lattice data with dimension 6 and 8 and the known dimension 4, because that would tell you more about, is it really slowly converging in dimension, or are the first few non-chirally suppressed contributions enough to do it? My guess is it'll be very slowly converging, but it would be really nice to know explicitly.
I've never thought about it in that way, so I haven't attempted to fit the lattice data. Because there are too many parameters, but still, like you said, it may be possible to obtain something from there. And you have some experiences about that.
I think it would be an interesting exercise. I expected, sorry. My first guess, based on experience with the vector and axial vector two-point functions, would be that you wouldn't really fit the data better for a much bigger region, but we don't know that. And if you did a fit with just dimension 6 and 8 and the known dimension 4, and it worked for a wider range, that would be interesting, because it would say that the V minus A OPE is actually converging relatively quickly at low dimension. I don't think it's probably the case, but if it's not the case, you would certainly see that by including dimension 8 in it would not change the picture hardly at all.
Okay, thank you.
So how bad is actually the rotational symmetry breaking when you take direction along a lattice spacing? How bad is this?
I'm sorry, which is symmetry breaking?
Well, so you said that you eliminated the points along the lattice direction for the continuum limit. So how bad is it when you take them into account? Or?
How bad? Very bad. Actually, maybe orders of magnitude, but already in the logarithmic scale, I see the variations.
But does this happen when you compare different angles, or does it also happen when you only compare along the lattice direction?
If I take the x direction, for instance, I see very strong lattice spacing dependence that I don't even want to try to extrapolate. But that's very different for depending on the angles. Yeah.
What was your lattice cutoff in these simulations?
2.4, 3.6, and 4.5 GeV. So fairly fine lattices.
So one question I had was whether the lattice data points that are shown in these plots, are those taken at different, are these from different lattice spacings and somehow extrapolated already?
That's after the extrapolation.
Okay. And then
not very nice, but extrapolation is like this, from the causal lattice to the final lattices.
And then my other question was, you chose different bin sizes. That's what you showed in the plot that just before. What were the criteria? I mean, was this just trial and error to see that you get? How did you choose the bin sizes to be different? In the other plot that we were looking at before.
Yeah, I do not really remember. That's actually that's the more like a difference of the coefficient in the continuum extrapolation than the bin size. I mean, in this region, in the small x region, the coefficient towards the continuum limit is too large. And so we decided to eliminate those. I mean, coefficient is too large, and also there is significant deviation from the simple linear extrapolation in A squared in that small x region. So we attempted many different things, but inspecting continuum extrapolation with various bin sizes, we decided that these points are not reliable. So I chose this plot because for some reason. But anyway, that is more about the reliability of the continuum limit.
So I was wondering if you choose bigger bin sizes, the blue points have the bigger bin sizes because that improved the continuum limit?
Not really, not really. But at shorter distances, there is fewer lattice points.
Yeah.
So
so you just
by choosing the two small bins, the lattice data simply just jumping around.
Okay.
Yeah.
Any other questions? Okay.
Can you go back to your slide on the BLM scale setting? The one with the plots. I have to say that I am absolutely terrified by your left plot.
I'm sorry?
I am absolutely terrified by the left plot. How can it be so bad and how can it be so good after? I don't know. I mean,
I'm not sure if I could catch the question.
Yeah, I didn't ask anything yet, but it looks like I was saying that I was terrified by the left plot and amazed by the second plot because it looks like there are some large log that you are not summing up on the left plot.
My conclusion is the opposite. I mean, you go to 0.1 Fermi, which is 2 GeV, everything's converging.
But are you taking your mu? Shouldn't it be like 1/x?
Mu to
make
be
sure
1/x.
It's over with 1/x.
On the left hand side, yes.
Get it that bad, and
that's very different from the other
yes.
ones. That's 2 point something over x. I thought. Yeah.
I don't know. Well, I don't know. It just works.
You mean that
it's
well, too good?
It's
or
too good and too bad.
Or the original suggestion was too bad.
Well, since we are here, because what alpha do you take? I mean, this 0.5 Fermi is 400 MeV. 1 Fermi is 200 MeV. So now I understand that you are making an expansion in powers of alpha at mu star. Okay. But mu star, what is the value of mu star?
I don't remember, but it was something like 2 point something over x. So at 0.5, it's still more like 1 JeV.
So you mean that each value of x, you are using a different mu?
Right. Yes.
Okay. And then, let me. Have you tried? Now we go to. Have you tried to? I mean, you have this lattice determination of this correlator.
Mm-hmm.
You have perturbation theory to order alpha to the fourth. Have you considered to take your lattice determination minus perturbation theory and to see what is the scaling in x? I mean, it goes. What is the power? I mean, if you have already reached the subleading, the non-perturbative correction should scale like x to the fourth.
I need to think about that. Yes. Okay. I'm not so sure.
Because for the plaquette it has been done.
Yeah.
Can you show again this transparency where you have the comparison with the spectral function of Aleph?
Spectral function of...
You had a plot with the spectral function of Aleph for the vector channel, I think.
Yes.
Yeah, the one before? No, you passed it. No, spectral function.
Passed.
Yeah, that's the one. So that's for the vector channel. Do you guys have the same for the axial channel? The right
we did it. We did the same thing for the axial channel. Yes.
Then you can check the Weinberg-Sum rule.
Weinberg-Sum rule.
Yeah. So the integral of the spectral function for vector minus axial should be 0.
Or f pi or something. I don't remember.
Well, yeah. Or f pi squared. Yes, depending on whether you include the pion in the axial channel or not.
Yeah. It's an interesting suggestion. Yes.
Okay. Any other questions?
So in the extraction of the core condensate from these current correlators, you're using the tree-level matching coefficient on the perturbative side. Did I get that right?
I have to check. But if I remember correctly, this is a direct consequence of the axial word identity. So I think I don't need any extra
So you're saying
coefficient.
there are no perturbative corrections to that?
Yeah.
Okay.
Any other questions? I myself, I have another one, maybe.
Could you? I'm sorry. I'll go ahead. Yes.
No, I can. Could you go back?
Back or forward?
Back in the formula that you have. I mean, maybe it's forward to get the. I mean, you have from experiment. Next one, this one. I mean, for the raw, I understand that you will have only experimental data up to a given scale. What do you do for higher scales to use this formula?
I think above 2 point something Jeb or 3 Jeb, I switched to the perturbation theory.
Okay.
Plus the duality violation models.
Okay. Okay. Any other questions? If not, let's thank the speaker again.
Thank you very much.